Hello everyone, my name is Nidhi, Dr. Nidhi Gupta. Today we will be discussing about one of the complex topic in data structure, that is the binary search tree and the AVL tree. So let's discuss the binary search tree first. So binary search tree is an ordered binary tree. As we know that the binary tree is having at most 2 child nodes. So there can be no child node, one single child node, as well as 2 or a maximum 2 is permissible in binary tree. So in that case, the insertion and deletion in the binary tree can be take place in any order, just the condition of at most 2 binary tree should be met. So there arises some problems in case of binary tree, as whenever we need to search in a binary tree, then in that case the elements are not ordered. So in that case, if the tree there is a node and we have the left subtree and the right subtree in the node, so we need to search each and every element in the binary tree in order to get the search successful. So the time complexity for the binary tree searching gets increased to big O of n. Whereas in case of binary tree, we actually go for the complexity of big O of log n. So in order to maintain the time complexity of big O of log n, we try to make the tree, we create the tree in an ordered way, so that the search complexity can be reduced to log n. So let's discuss this binary search tree. So the binary search tree is also known as an ordered binary tree, is a variant of binary tree in which the nodes are arranged in order. And what the order is, that all the nodes in the left subtree are less in value as compared to the root node, and all the nodes in the right subtree should be greater than or equal to the root node. So the elements in the binary search tree are arranged in this fashion. We called it as a ordered tree or the binary search tree. So let's take this example on the screen. So it is showing that over here the 8 is the root. As 8 is the root, we have 3 at the 3 is the left child, 10 is the right child. So we can see that 3 is less in value than the 8 and 10 is having the greater value. So this thing is recursive in the binary search tree. It means that the same thing continues within the subtree as well. So for the root 8, we have this subtree. So this is the subtree. This is the left subtree for the root 8 and this is the right subtree. So in the left subtree also this property holds true, and in the right subtree also the same binary search property should hold true. So in this case we see that 3 is the subroot and the elements at the left side is having the lesser value than 3 and the elements at the right side is having the greater value. So over here 6 is greater and 3 is lesser than 1 is lesser than 3. So we see, if we see the subtree of the subtree, then 6 is the root, 4 is having the lesser value and 7 is having the greater value than 6. So all the nodes at the left of the 8 are lesser than the 8. Similarly, all the nodes at the right side of the 8 are having the greater value. So this is an ordered, their elements are stored in an ordered way. So I have said that the average running time of a search operation is big O of log n, as at every step we eliminate half of the subtree from the search process. So if we are having n elements, at every step we are dividing the elements by 2, so it becomes n by 2 and n by 2, and we are searching at a single side only. So the time complexity gets reduced to half at every step. So due to its efficiency in searching elements, binary search tree are widely used in many applications just as dictionary based problems. So we have the binary search tree. So let's create a binary search tree using some example. So over the screen, some values are given to us, just like 45, 39, 56 and so on. So these values, we want to create a binary search tree for these values. So we go it in a step by step manner. So the first element is always acting as a root. So first of all, we always consider that the tree is empty right now, and thereafter we insert each element one by one. So 45 being the first element becomes the root, then 39 being lesser than the 45, it goes to the left side of the root 45. Then we have 56. So we compare this 45 with 56, and 56 being the larger value than 45, it goes to the right side of 45. Similarly, if we go in this fashion, so we have the 12. 12 is lesser than 45 and it is lesser than 39, then we go to the left side of 39. Similarly, 34 lesser than 45, lesser than 39, greater than 12, we go to the right side of the 12. 78 being compared with the root first, again 45, then 56, and then we have 78 being greater than the 56, go to the right side of the 56. So this continues with the other number 32 we have over here. Likewise, we have over here 10 and then 89 and 54 and then 67. So these are the elements that are stored in a binary search tree order. Now we need to perform some operations in the binary search tree. So the first operation in any of the data structure is the searching. So searching is to find out the desired element in the given list of elements. So over here the data structure, we are having a tree, that is a binary search tree. So we know that the elements are in a binary search tree are stored in an ordered way. So likewise, when the elements are stored in an ordered way, it is easy to fetch the elements because they are in an ordered way. So the searching function means to find whether the given value is present or not in the tree. So the search process begins always with the root node. The function first checks if the binary search tree is empty or not. If it is empty, then search is not possible, and if it is not empty, then we go for it. We compare the element to be searched with the root node, and if the element is found, we say that the element is found. Otherwise, we compare the value with the root node if it is lesser or it is greater than that, and thereafter we proceed in the same way. So the algorithm over here is showing the concept of searching in a binary search tree. So in the step 1, we say if the tree of data, here tree is the name of the pointer, the root pointer, initially the value of tree would be root and it is being taken by the user only. So it is a function. So this tree data, if it is equal to val, then it means that the search is over now and we need to return. Or tree is null, it means that if it may be happen that the element is not present, then in that case tree becomes null, the pointer becomes null. Then in that case we return it as a tree only. So tree, if it is null, it returns null. If it is having some data, value is found, then the pointer is returned by this function. So this is the base condition for the recursive algorithm. So this is the recursive algorithm and this is the base condition, that either the search is successful or we are not getting any of the element. Else means that what we do if it is not there, we compare the value to be searched with the data part. So if the value is lesser, then we again go through this algorithm again, search element. The name of the algorithm is search element. Now in that case, instead of tree, we give the pointer as tree left, because the value that we need to find out is lesser than the tree data. Then in that case, over here tree of left should be sent instead of tree, and the value would remain the same that we want to search for. Similarly, the else means if this condition is false, then in that case the value is greater. It means that we need to go to the right side instead of left. So over here the recursive function is called, and this time the tree pointer becomes tree right instead of tree left. So and the value gets passed. So this is what the searching is. Now, insertion. When we want to insert an element in a binary search tree, as we did in the previous example, that every time we are searching, we are inserting a number inside the binary search tree. So what we do in that, we always compare the given number, the number that need to be inserted with the root node, and we compare the value with the root node. If the value is lesser, we go to the left, and if the value is greater, we go to the right. So over here also, as the algorithm shows, and it is again a recursive algorithm, so the base condition is also there. So we say if tree is equal to null, then it means tree is equal to null means if the tree is either empty or we are not finding the same element inside the tree. So it means that we are now able to insert the element in the tree. So then we allocate a memory for the tree, and if it is the tree is a pointer which is pointing to the new element, then we insert the value inside the data part of the tree. Tree data equals to val, and then if whenever we are inserting any element, that would be the leaf node. So the left child and the right child becomes null. So let's see this. Tree of left becomes null and tree of right also becomes null. So whenever we are inserting the element as a leaf node. Else means that if we are not coming to the end of the any of the tree, means we are still finding the place to insert, then obviously we need to keep traversing according to the value. We need to go to the left or the right until we find the desired location to insert. So over here, if value is less than tree of data, we call the same function insert, and over here we pass the pointer instead of tree, we pass the tree left, and the value becomes same. Similarly, else part, we find the value, we find the pointer as tree right instead of tree. So the value becomes same. So this process continues and until we find the desired location. When we find the desired location, obviously the tree becomes null at that point because we are inserting at the leaf node. So then this memory will be allocated, and thereafter we insert the data. So this is the algorithm for binary search tree insertion. Now, after insertion and searching, we need to delete the element in the binary search tree. So the delete function, what it does, it deletes the element. Now over here we need to take care of the property of binary search tree, because whenever we delete any element, the property should remain hold. So in that case, whenever we are deleting any of the element, we need to check whether the element is having a child node or not. If the element that we are going to delete is a leaf node, then there is no problem. We can simply delete that as it is. Okay, but in case the element is having the child node, then in that case the cases may be that the element is having a single child or the element is having the two child. So we need to take care of these cases as well. So let's see the case 1. In that case, the case 1 says that deleting a node that has no child. So in case I want to delete any of the element such just like 78. So for deleting the 78, we know that there is no child node over here. Then in that case, what we do is we simply delete it. So nothing would, the property of binary search tree will remain as it is, and there is no loss over here. So we delete this 78 as it is, and we can see this is the leftover binary search tree with no element as 78. So this is the case 1, very simple case. The element is having no child. Now the case 2, what it says that deleting a node with one child, either left or right, any one child is there. Now what we do is, just like over here, if we want to delete this 54, now 54 is having a single child, that is 55. Over here we can see this is 54 and this is 55. If we want to delete this element, then what we do is, if it is having the single child, we replace this deleted element with that child. Simple. So in this case, let us see this, that 55 comes over here, it takes the place of the deleted element, that is the 54. So this is the case 2. Now the case 3 is that deleting a node with two children. So if a node is having the two children and we want to delete that node, what we do is, we would find out the in order traversal of that tree. Now in that case, when we find the in order traversal, the deleted element predecessor or the successor will replace that deleted element. Let's see the example. Suppose this is there, this is the example over here, and over here we want to delete the element just like 56. So this is 56, as we can see over here, this is 56, we want to delete this. Now let's write the in order of this. So in order is 39 left, root, right. Root is 45, then we go to the right, and then we go to the, for right we go to the left first, left, it is not having any left, so 54, then we have 55, then we have 56, and then we have 78, and then 80. This is the in order traversal for this tree. Now we want to delete this 56. So the rule says that we can replace this 56 either by 55, that is the predecessor, or 78, which is the successor. Both are correct. So in that case, this 55 over here, we can see that we are replacing this 56 with the 55 predecessor. So this is the 55, and this obviously when we replace it, then this should get deleted from here. So it is having no child, we can easily delete it, and it is replaced by this, and we get over this. So this 55 should also get deleted over here. Let's see like this over here, that 55 gets deleted and 55 goes over there. So in this way, if the elements is having the two child node, then we replace the element either by the predecessor or successor. So we can even replace it by the 78 also. So over here 78 is having a single child, 80. So what we could do is 78, then we could go for 80. This one is also correct. So both are correct. So we can do either of them. So this is about the deletion. So let's go for the algorithm, and in this algorithm we need to take care of all the three cases. So what we do is, if the tree is equal to null, then we say that either the searching has stopped and we are not able to find any element matching to our criteria. So we say that element not found in the tree and we are not able to delete that. Else we find the suitable element according to the search. So we compare the value with the tree data, we go to the left or we go to the right, like we did in the previous algorithms. So we keep on doing this. This is a recursive. Again, we also check if the left and the right subtree is there. Then in that case, what we do, if the element is having left and the right subtree both, it means that it is the case of the element when it has two child nodes. Then what we do is, over here we are finding the largest node. So we are going for the successor, not the predecessor. So we are finding the largest node. So this is the function which gives us the largest node in the tree, so that we can replace the deleted element with that number temp. So we get the location of that largest node. So tree of data is replaced with the temp data. So this is the case, and we again do the recursive with temp data, because wherever we are taking the data, it may happen that in that place also there is a single child or zero child or no child. So that is why we need to call it again. Else, set temp equals to tree, and what we do is, if tree of left is null and tree of right is null, it means that there is no child node, then we simply delete it, set tree equals to null. If tree of left is not equal to null or the right is not equal to null, means it is having a single child, then in that case set tree equals to tree of left if it is left is not equal to null, or tree equals to tree of right if it is not equal to null. And at last what we do, we free the temp. So this is the algorithm for deletion in the binary search tree. Now let's go for the AVL tree. We have seen that the binary search tree has the remarkable property that it is making the things ordered, and we are fetching it we are storing it in an ordered way, we are fetching it in an ordered way, and it reduces the search complexity. But not every time. There are the cases when we need to balance the tree, because the tree becomes unbalanced and it increases the search complexity. Let's take an example. Suppose I am having this tree, just like over here it is 30, then I am having the elements like this 50, I am having the elements like 80, 100, 110, maybe I am having these elements, these 5 elements, and obviously this is a binary search tree only. So in that case, whenever I want to find any of the element from this, then instead of big O of log n, the complexity becomes big O of n, because the tree is skewed. It is skewed in a particular direction. So in that case, what we do is, we try to balance this height. So the problem is the height. Over here, the height is 0 at the left side, but over here 1, 2, 3, 4, the height is 4. So we are in the process of making the height balanced. So the AVL, what AVL does is, it balances the height of a binary search tree, so that the time complexity of search becomes less. In the cases where the tree is skewed, it is tilted to a particular direction. So AVL tree is also called height balanced tree. So it is a self-balancing binary search tree in which the height of the two subtree may differ by at most one number. So over here, the property of AVL tree is that the left subtree and the right subtree should differ by one height, single height only. Over here, let's see this, the height is 0, over here the right height is 4. So the difference is 4. So it is not permissible in case of AVL. So AVL is named after the 3 researchers in this field, Adelson, Welsky and Landis. So they all gives this algorithm which balances the height. So it balances the height by finding out the balance factor of each node. So the formula for finding the balance factor is, the balance factor is equals to height of the left subtree minus the height of the right subtree. So we will find the balance factor of every node. So if the balance factor is 1, -1 or 0, then in that case we say that tree is balanced and there is no need to balance this tree. But in case the balance factor is apart from this 1, -1 and 0, then in that case we say that this tree is not balanced and we need to balance this tree. So let's see how we can do this. So this is the example over here. We say 0, 0, 0 is indicating, this green is indicating the balance factor. So let's take any of the nodes just like L. So L, the height of the left is 0, height of the right is 1. So 0, so height of the left is 0 and the height of the right is 1. So we say that the balance factor is 1 over here. Similarly, height of the over here, the height is -1, there is a 0 height, left and right both are 0. So when we minus it, it becomes 0. So over here we can see that the height of the left and right is at most differ by 1 only. There is no much difference. So in that case, this tree is said to be balanced. So the search operation for the AVL tree is same as the binary search tree, no difference in that. We search it in the same way, we compare it with the root node with the value, and either we go to the left or the right, and the complexity becomes big O of log n. Now insertion in the AVL tree. So insertion is done in the same way as we did in the binary search tree, but again over here we always take it into account the balance factor. On every insertion we need to calculate the balance factor. If the balance factor becomes 1, -1 and 0, then we keep on doing the insertion in the same way as the binary search tree. But if the balance factor becomes 2, -2, +2, -2, then in that case we need to first resolve this by doing some rotations, and then we proceed with the same way with the insertion. So over here in the insertion, we need to do some rotations while insertion. So there are 4 rotations that we need to perform: LL, RR, LL, RR, LR, RL. LL says the new node is inserted in the left subtree of critical node. Similarly, RR is new node is inserted to the right subtree of critical node. So what happens is, when we have a tree and if suppose the tree is balanced, then there is no problem. Again, if I am inserting any element and tree becomes unbalanced, it means that some of the node, maybe 1 or 2, is getting the value balance factor as 2. Then when we are inserting any node, we see the unbalanced node from that inserted node and we call that node as a critical node. Now this critical node is the unbalanced node basically. So what we do is, by seeing the position of the insertion and by seeing the critical node, we will see that which type of rotations is possible, either LL, RR, LR or RL. So let's see this example. So we are having this tree. Over here we can see the balance factor is 0, 0, 0, 1. Then again we have 1 and this is 2. Okay. Then in that case, actually this is again 2, 1, 2, 0. The balance factor is 0 because HL is 1, 2, 2 HR is 1, 2, 2. 2 minus 2 is 0. The balance factor is 0 over here. So it is 0. Then, in that case, when we insert 7, so 7 is inserted over here. We will insert over here 7. So we see, again we calculate the balance factor. So it becomes 0, it becomes HL is there 1, then 10 becomes 2 because HL 1, 2, 2 and HR is 0. So HL minus HR. So 2 minus 0 is 2. So balance factor of 10 becomes 2. Now insertion takes place over here. And on inserting this element, this node becomes unbalanced. So what we do is, we see the critical node. This is the critical node, we mark it as A. So this is the critical node and the insertion takes place to the left of A. Then in that case, the rotation would be LL, left subtree of left child. So over here, left child of A is 9 and the insertion takes place to the left of 9. So we perform LL rotation. So LL rotation says that insertion takes place from this side, then we rotate in this way. So over here, this is A and the element immediately below A becomes B. So over here, B takes the place of A. So over here we can see it is B, it was A earlier. So the rotation will take place like this and B takes the place of A, and this is the balanced tree now after doing the LL rotation. So we can see the balance factor is 0, 1 or minus 1 only over here again. Another example, let's see. This is LL. Similarly, we can see over here that on insertion of 8, the tree becomes unbalanced. So this A becomes 11 becomes A because insertion takes place over here. We go to the root and we find this first unbalanced node. It becomes a critical node. Then the node below A becomes B. So the insertion takes place to the left of A and left of B. Then again we perform the LL rotation, and in that case on LL, B takes the place of A. So again we can see that over here the rotation would be like this, and 9 goes upwards, A becomes here, 9 B over here. So the tree is balanced now. So this LL is RR is same as LL, just the difference is that over here the insertion takes place to the left of A, and in case it would be right of A, then in that case it becomes RR, and LR and RR both are same. Over there the B takes the place of A, and LR and RLR, they both are same. LR and LR and RL, these both are called double rotation. So left subtree of right child of critical node and right subtree of left child of critical node, in that case they are double rotation. In that case we find out the C also. So let's discuss this. On insertion of 15, the tree becomes unbalanced. Now balance factor over here 0, HL minus HR plus 1, HL minus HR minus 1, then 1, 2, 3 or 1 plus 2. Now in that case insertion takes place over here. On going to upwards, first unbalanced is this 50, it becomes A, now this becomes B, and when we see insertion takes place over here, it becomes C now. So A, B, C. So left of A and right of B. So the rotation is LR, left of A and right of B. Then in that case C takes the place of A. So let's see over here 20 goes upwards, C becomes over here. So why it happens is, like over here the double rotation takes place. First the rotation takes place through B, and then thereafter the rotation takes place through A. So likewise the resultant would be that C comes in the upward direction, and A comes over here. Similarly, the B remains here. So this would be the tree, resultant tree on performing the LR rotation. Similarly, RL is also same as LR. So in the same way, like left and right, this is LR. In case it would be right and left, it becomes RL. And in that case also the C takes the place of A. So both LR and RL both are same. Now in case of deletion, this was the insertion. The 4 cases were there: RR, LL, LR and RL. In case of deletion, there are 6 cases. Quite easy. Basically, they are categorized as R and L. R, we have 3 cases: R0, R1, R minus 1, L0, L minus 1 and L1, like this. These are the rotations. So whenever we are going to delete any element and thereafter the tree becomes unbalanced, then we go for balancing the tree after deletion. So just like this is the example over here. So over here we can see that we are going to delete 72. So this is 72. This square box is showing the balance factors and this circle is showing the value. 72 is here and having the balance factor 0, and over here we can see the tree is balanced right now. But after this deleting this, the balance factor, let's see, becomes 0, it becomes 2. So 45 becomes unbalanced. Similarly, all are balanced but 45 becomes unbalanced. So in that case, deletion, this becomes critical node. Now deletion takes place to the right side. So we say that R would be there. Deletion takes place to the R of A. Now this is the case of R, but this is the case of 0, -1 or 1. It is decided by the balance factor of B, and B is taken in the opposite direction of the deletion. So the deletion direction is here, so B is here. This would be the B. So over here the B balance factor is 0 after deletion, so this case is R0. Now if this is the R0, we perform the R0 over here. The B takes the place of A, nothing else. So this becomes B. We know at rotation takes place like this. So 36 takes the place of A. This is 36. Over here this becomes A, and likewise we arrange all the elements by doing this rotation. So we can see over here that this is again becomes the balanced after performing R0. Similarly, if the balance factor of B becomes 1, then the rotation would be R1 and it is as same as R0. And if the balance factor of B becomes -1, in that case we go for C as well. So this C would be this. Then in that case C takes the place of A in case of R -1. So this is the case of R1 and this is the case of R -1. Over here we can see that this was A, the balance factor, because on deletion of 72 the balance factor of A becomes 2, B becomes -1 and C is 39. So I said that C takes the place of A. So in that case this 39 goes up because rotation would be first in this way and then in this way. Then the resultant tree would be the C takes the place of A. Then this is 39 and likewise we are having all the elements. So this is R -1. So L0 and L1 both are same. The difference is of right and left. If the same thing, the deletion takes place towards the left, then we say it is L0. Then if the deletion takes place towards the left and the B would be 1, then we say L1, and R -1 and L -1 are same. So this are all the 6 cases of deletion: L, 0, L1, L minus 1, R0, R1, R minus 1. And of course, this AVL tree is a binary search tree only, is having the property of binary search tree. So that's all about the insertion and deletion in AVL tree and about the binary search tree.